My name is Thomas Beckers. I'm a postdoc at the University of Pennsylvania, and today I want to present our paper, Gaussian Process Port-Hamiltonian Systems, Bayesian Learning with Physics Prior. So the motivation of this work is basically driven by the fact that the modeling of electromechanical systems becomes more and more challenging over the recent years. Here you can see two examples. On the left side, a humanoid robot from Boston Dynamics. On the right side, a bio-inspired robot from Festo. And you can imagine that the modeling of these systems is quite challenging. At least it's very time-consuming, using first principles, and required solid expert knowledge. So there's a need for expressive models which should be on top, reliable, and well generalizing, as we typically want to use these models for the design of a controller at the end. So we got the following problem statement. We consider here an electromechanical system with x dot equals f of x plus gx times u, so it's input affine, and we are able to collect some state measurements which can be corrupted by Gaussian noise. And these measurements are used to create a data set, and each point in this data set consists of a timestamp t, the noisy state measurement x tilde, and the applied input u. The problem is now, given this data set calligraphic D, we aim to find a dynamical model that first is able to represent a large class of systems, so it should be expressive. It should allow uncertainty quantification so that we know if the model is trustworthy or not. And finally, respects physics so that it generalizes well even for areas without training data. And before I present our approach, I want to give a brief overview about the related work. So there's a long history of using data-driven approaches like neural network or Gaussian processes for the modeling of dynamical systems, which are expressive and sometimes provide uncertainty quantification, but do not include physics. Then there is recent literature about Hamiltonian neural networks, for example, or neural ODE, which allows to include physics, but do not provide any uncertainty quantification. And then there are some approaches using machine learning models with uncertainty quantification and including physics, but often limited to not very expressive models. So we aim to close this gap to get an expressive model with uncertainty quantification and including physics. And we do that by combining Gaussian processes with Port-Hamiltonian systems. So let me start with introduction to Gaussian processes. So Gaussian process is basically a distribution over function space, which is fully defined by a mean function m and a covariance function k. And using Bayes' rule, we can compute the posterior distribution based on collected data. On the right side, you see the mean function and the covariance function. So here's a prior. And then using collected data, the uncertainty is reduced in this area. And here you see the colored lines are some samples of the Gaussian process. And with more and more data, our model gets more and more confident. And at the end, if we want to compute the output for a new test input x star, it is a Gaussian distributed variable. So based on the data of the input data capital X and output data capital Y, we get a closed form solution for the posterior mean and the posterior variance here. And the posterior mean is given by the covariance between the test input and the input training data capital X, the covariance of the input training data, plus the variance of the noise, sigma here, times the output data capital Y. And we also get a closed form solution for the posterior variance. And another interesting property for us of the Gaussian process is that it's closed under linear operators, which means if we have a linear operator calligraphic G and a Gaussian process G of X, then f of x is a Gaussian process as well, because we can include this linear operator into the Gaussian process. So now about the physics model. So we know that the trajectory of a physical system lies on some manifold because we have some physical axioms in the background. And an expressive class of physical systems can be is given by Port-Hamiltonian systems. And here we use a Hamiltonian system which defines the total energy in the system, H, and interconnection matrix J, which defines the flow of energy inside the system, for example, the flow between potential and kinetic energy, a dissipation matrix R, an input U, an input matrix G, and an output Y. This interconnection matrix J is skew-symmetric, and so it's ensured that we have energy conservation if the dissipation matrix R here is 0. The input U and output Y defines a passive system. So a Port-Hamiltonian system is always passive. We can connect a Port-Hamiltonian system with another Port-Hamiltonian system and this preserves the structure. And it's suitable for multi-domain applications. So for example, we can connect an electrical system with a mechanical system using this idea of energy flows. So now how can we combine this with the Gaussian process? We start with some physical system, we collect data, and then what we do is we put a Gaussian process prior on the Hamiltonian function, because the Hamiltonian function typically includes the nonlinear dynamics of the system. And we assume that we have some structural knowledge about the interconnection matrix, the dissipation matrix, and the input matrix G. So, but what we can do is that we can, or we assume that we might not know all parameters in these matrices, but we can then estimate these parameters. And this gives us a physics-informed Gaussian process model, which is actually a distribution over Port-Hamiltonian systems. So all Port-Hamiltonian systems under the GP prior on the Hamiltonian. And in detail, what we do is we start with a system, we collect some measurements, and then we use another Gaussian process to transform the time state measurements to state derivative measurements. And with the state derivatives, we can, and the estimates for the J, R, and G, we can then construct our GP-PHS. And after the training, we can sample from this GP-PHS, we can sample Port-Hamiltonian systems. And then we have to do some approximation of the Hamiltonian, which I will talk later about this approximation. And then we use an ODE solver to get our trajectories. And so we end up with a model which gives us a distribution about Port-Hamiltonian systems based on the collected data. So let me start with the training process. So we have a set of timestamps and noisy state measurements, and then we use a Gaussian process to predict, on the one hand side, the state, so without the noise, the state X, and on the other hand side, we want to predict the derivative of the state. And we can do that because we can include the partial derivative as linear operator in the Gaussian process. Then we create a new data set of state and state derivative pairs and call that calligraphic dx. Then we use this data set for the Gaussian process Port-Hamiltonian system with the structural estimates of G, R, and J, R, and G. So we put a prior about Port-Hamiltonian systems, which is defined by a Gaussian process with the mean G hat times U and a Port-Hamiltonian systems kernel. And this kernel is shown here. So it's basically a squared exponential kernel for the Hamiltonian, because we know that the Hamiltonian is a smooth function, and then we include the linear operations of the Port-Hamiltonian system. So the partial derivative and the multiplication with J and R here. Now to compute the unknown parameters in our matrices, we first collect all the parameters. So phi j, phi r, and phi g are vectors of the unknown parameters together with the unknown hyperparameters of the kernel function of the squared exponential kernel. And then we can minimize the negative log marginal likelihood here, like as in standard Gaussian process training. The main difference here is that now as noise, we use this matrix delta, and this one is given by the first Gaussian process, which predicts the uncertainty, or which gives us a posterior uncertainty for the state derivative. So we include this uncertainty of the Gaussian process in the first stage in this Port-Hamiltonian Gaussian process. And at the end, this Port-Hamiltonian systems kernel creates us a distribution over Port-Hamiltonian systems. Then, in the second part, we can sample from this model. So what we do is we sample a Port-Hamiltonian system, and we use here the fact that a Gaussian process follows a multivariate Gaussian distribution. So based on this training data, we can sample a Port-Hamiltonian system with the Port-Hamiltonian systems kernel. And at the end, what we want to do is we want to then use it in an ODE and then solve this ODE. So here on the right side, this f hat is now a sample, which is indicated by this parameter omega. So that's a deterministic function. The problem is now that f is some vector field, but for the numerical integration of the ODE, we need to have access to this vector field at any arbitrary number of points at arbitrary locations. However, this function f is not callable, so we can only predict this f for a known set of finite points. So what we do is we do some approximation, but not for f, but for the Hamiltonian h. And we do it for the Hamiltonian because if we would approximate f, then we might lose the physical structure of the Port-Hamiltonian system. Therefore, we sample a Hamiltonian, and then we approximate this Hamiltonian to get a callable function. And as function approximator, we can use, for example, spline approximation or other function approximators. And then with this approximation, h hat star, we can use an ODE solver with our matrices J, R, and G, and then we can generate trajectories. So to summarize it, so we use here an approximation of the Hamiltonian H to get a callable function for the ODE solver and to preserve the structure of the Port-Hamiltonian system. And as theoretical results, we can show that for this Gaussian process Port-Hamiltonian system with this data set calligraphic dx and a smooth and bounded approximation of the Hamiltonian, that then these ODEs here describe a Port-Hamiltonian system which is almost surely passive. And it's almost surely because of the probabilistic nature of the Gaussian process. And second result is that we are able to preserve the interconnection property. So if we have two Gaussian process Port-Hamiltonian system, we can do a feedback interconnection, and we end up again with the Port-Hamiltonian system. And this allows us to do some composable learning. So if we have a large system, we can compose it in subsystems and learn these subsystems, and then later connect these subsystems again to get the whole system. Okay, so we performed some simulation for this idea. In this case, we had a ball in a magnetic field, so with a coil, and we turned this coil on and off. And so, and you see here the position of the ball over the time. And in the dashed line is the ground truth. So we have some oscillating behavior here. The colored lines are now samples from the Gaussian Process Port-Hamiltonian system. And as baseline, we use a vanilla Gaussian process to learn the dynamics. And we only have around 400 training points here from only one trajectory, observed trajectory of the system. And you see that we can quite accurately model the position, momentum, and magnetic flux of the system. And here on the right side, you see now the Hamiltonian function. So for all these samples, and again, the dashed line is the ground truth. And the interesting part is here the right side. So when the input function is 0, we expect to see a decrease of the energy, because without any input, the energy must be static or decreasing. And in this case, you see it's decreasing. So that means that all these samples represent physically correct systems. So with this Port-Hamiltonian systems kernel, we can encode this physical prior knowledge of energy conservation or dissipation into the GP model. So to conclude my talk, I showed you that Gaussian process Port-Hamiltonian systems generate all possible realizations of over Port-Hamiltonian systems based on the collected data. We are able to preserve the interconnection property and the passivity characteristics. And this model is physically correct in terms of the energies and allow uncertainty quantification. Thank you very much for listening. And if you have any questions, feel free to send me an email or to browse on my website. Thank you very much.